box over here is the actual well that goes down to the ground. And in there is a 15 horsepower, 3-phase 240 pump. The well is located about 400 feet down, and there's a 3-inch line coming from the pump all the way to the surface. And then it makes a turn, and then it goes into this 10,000 gallon tank. If for some reason you needed to get that well out of the ground to get access to the water, you would have to pull the pipe and the pump out of the ground, and it's approximately 2 tons in weight, so it requires a crane in order to get there. This is a 10,000 gallon water tank that supplies the needs for 3 houses, and you know, in an emergency they have this supply. In this building over here are the pressure pumps, and there is a main pressure pump that is 3-phase for the supplying pressure for the 3 houses. There's also a backup pump that's attached to a generator. We're going to go over and look at the generator in a second. Okay, here we have a typical backup generator situation. This is a 20,000 watt generator that will kick on if the local power from the utility company were to go down for whatever reason. Over here is a 500 gallon propane tank. Now, what a lot of people don't understand is if you put on this generator and it runs at its capacity of 20,000 watts, and this supplies the power to a large house, that the propane tank will last about 5 days. That's it. A lot of people don't even use that much propane in a winter warming their house. Yet, this particular situation, just to supply backup power, will consume that entire tank in 5 days. These are things to consider when you look at what your energy requirements are if you plan on having systems in place in order to compensate for local power going down. Here is the power switch that switches over from the utility company over to the backup generator. The mains in this case come out of the ground, which is actually a pretty good thing, because if there were a EMP pulse, where the wires go down into the ground, that's where the arcing and sparking would be, and this house would be pretty much safe from long wave EMP effects like from a solar storm or a nuclear pulse. People who have wires come directly to their house have no insulation and no ability for the arky-sparkies to actually dissipate before it gets to the house. So in this particular case, it's actually safer than most installations. However, if energy does get into this system, the circuit breakers and even this disconnect switch will not prevent those high voltages from arcing across the contacts and then going into the house. Here we have a rather large solar panel, and there's a motor control in here that actually turns it around and points it to the sun and actually tracks it throughout the day. One of the issues that the owner of this panel has is that when an electrical storm comes near, even though it doesn't get struck by lightning itself, if the storm is close by and there's a nearby strike, the controller, which controls the motors that turns this thing, blows out. And in some years he's had to replace the controller 3 times. So these are issues. Also, this is coupled directly into his system inside the house. on this configuration, this is pretty much the worst case setup for a long wave EMP pulse that would come down the main electrical wires. It would enter right in the roof of your building, and it would come right into your panel. If it was a long-term, let's say 1 or 2 days event for a solar flare, let's say, and it was energetic enough in order to really push down energy out of the wires, something would burn out. And one of the first things that would burn out would probably be your ground wire. A lot of times the ground wire is not even as big as the wires that come in to the building. So if you think of, what in here is the fusible link, the thing that's going to break first. A lot of times, I'm guilty of this myself, we don't have a ground wire that is larger than the wires going into the building. So if you truly had a very energetic system coming down your wires, it would definitely take out the smallest wire. In a lot of cases, the ground wire would be the first thing to go. And if that happened, then all of this, all of your electrical panel, the wiring, all of it would be energized at the whatever voltage was coming down the wires. That could be hundreds of thousands of volts. And then you would start arcing and sparking and everything else. Now you do not have the high voltage insulators on this building like you do on the telephone poles or the electric poles. So what would happen is, as the voltage builds up in the wires, it's going to find the places where it's going to have the least gap to jump. And if your house happens to be that spot, then what's going to happen is you're going to get arcing and sparkies, possibly on the roof, inside the wires, maybe inside your walls. Very, very bad situation. And so one of the things you want to do is you want to consider how the electricity is going to couple from the outside world into your structure. That's going to be your shelter in an emergency, and you don't want anything to happen to it. Well, here we have a situation where the power lines come into the pole, they come down into the box, but the good news is here they come out of the box into the ground, and then a short distance away is the actual house. And so if anything major were to happen and this starts really getting those high voltage spikes, even if it makes it through the box, it's going to come down in this ground and it's going to dissipate out. It's going to find the path of least resistance. And in this case, it's probably going to shelter your house from the effects of a solar storm, possibly even the effects of a nuclear blast, at least on the long wave stuff. And so this is a pretty safe situation. Obviously, there could be some more done, but for right now, this is the kind of thing that you want. You want somehow to place your wires underground for some distance before you get to your house. And where you've just covered the situation where the wires go directly to the house, and then that's a real problem. And there you need some added measures in order to provide a path for any of the energy that might come in to go around and circumvent going inside the structure. You got fakes on the trees too, Stark. This is a typical greenhouse that here in the high desert in Arizona. This particular one is buried about 4 or 5 feet in the ground to insulate it in the winter. This extends, it reduces the amount of energy to get it warm in the beginning of the spring, and it extends the growing season so that you can have probably around 9.5 months worth of growth in this environment.